Okay, let's consider that we've got some conductor and it's got some surface charges given by sigma. I want to look and determine what the electric field is at the surface of this conductor. So what we can do is we can first of all draw our Gaussian pillbox. And this Gaussian pillbox is going to have some surface area A. So now Gauss's law dot dA is going to be equal to sigma over epsilon naught times this area. We have to consider what happens above and below. So to work this out, what we have is the perpendicular component of the electric field above minus the perpendicular of the electric field below the surface is going to equal sigma divided by epsilon naught. Or we can write this in a slightly different way. We have our electric field vector above minus the electric field vector below is going to equal sigma divided by epsilon naught n hat. And n hat is our unit vector which is perpendicular to the surface of our conductor. Now what we notice here is that the electric field is discontinuous on going from above to below the surface. Now although the electric field is discontinuous across the surface, the potential is continuous, since we can write the potential above minus the potential below as the line integral from A to B of our electric field. Now what this tells us that is A and B come closer together as the path length gets shorter. What eventually is going to happen at the surface is V above is going to equal to V below. Now if we go back to our electric field above and below, we can write this in terms of our potential. So since our electric field is equal to the minus the gradient of our potential, what we get here is the derivative of potential dN. Okay, so that's the distance away from our surface, and this is above, minus the derivative of the potential, Bn, and this is below. And this will be equal to minus sigma over epsilon naught. Okay, so that's a quite a nice expression for the difference in the potential above and the potential below. We see that it's just equal to minus the surface charge divided by epsilon naught. Okay, so here now what we have are two boundary conditions for our conductor, and since the fields are inside a conductor is zero, the conditions require that the electric field immediately outside the conductor, E, is equal to sigma over epsilon naught by the unit vector n, again which is perpendicular to the surface. And it also means that our surface charge sigma can be written in terms of potential. So we can have our sigma is going to be equal to minus epsilon naught by the derivative of potential with respect to n. And n again is our distance away from the surface. So now in the presence of an electric field, a surface charge will experience a force. But since the electric field is discontinuous at the surface, there's going to be a force both above the surface and below the surface. Okay, so what do we do here? Well, essentially all we do is we've got our force will be equal to the sigma, the surface charge, times our electric field. And what we're doing here is we're taking the average electric field. Okay? So this is going to be equal to 1 over 2 times sigma by the electric fields above plus the electric fields below. And since we can write the electric field in terms of sigma divided by epsilon naught, we can now also write the force as equal to 1 over 2 epsilon naught by sigma squared in the n hat direction. Now what this force essentially amounts to is an electrostatic pressure which is acting upon the surface of the conductor. So we can write out this electrostatic pressure in terms of the electric field, and it's given by epsilon naught divided by 2 times magnitude of the electric field to the squared.